Today's video is going to go over 5 series related topics, which are geometric, divergence test, integral test, telescoping, and approximations. And what you need to know about geometric is that it is a constant ratio r, and with that ratio, if the absolute value of that ratio is less than 1, the series will converge, and if it's greater than 1, it will diverge. So if it does converge, you will use a formula where s equals the first term over 1 minus the ratio. The next test is the divergence test, which is the first test you should do, and it's basically just taking the limit, where if your limit of a sub n is not equal to 0, it will diverge. But if it is equal to 0, you need to do a different test, probably the integral test. Speaking of integral test, we will connect using series with integrals, but when doing this test, you have to state whether it is positive, continuous, and decreasing, which I will show you how to prove. And then once those tests are completed, you have to do an evaluation on an improper integral of your series, where the k is the n from your series, which is shown here. And if your integral converges, your series will converge. But if your integral diverges, your series will diverge. Now, a telescoping series is where most of the terms cancel out from writing the sum, which usually requires a partial fraction decomposition. And an example is 1 over n minus 1 over n plus 1. And so what you would do is you would write out your s of n, which is a summation, and you would write out all of your terms, but then you start to notice that the middle terms will cancel out. So this negative b2, and then this b2 will cancel out, this negative b3, this b3 will cancel out, this negative b4, and this b4 that's going to be eventually in here will cancel out, and you're going to be left with the s of n equals b1 minus bn plus 1. And so lastly, you will take the limit of n approaching infinity of this s of n. And lastly, approximations, where this is typically an integral test for convergence, and you will be given an error tolerance of, for example, less than 0.0001, where the goal is to find how many terms are needed. And all of this will be demonstrated in today's video. Now our first series is going to be the summation of 2 to the power of 2k minus 1 over 9 to the power of k plus 1. And our starting term will be 1, and it is an infinite series. Now we could rewrite this as 2 to the power of 2k times 2 to the power of negative 1, all over 9 to the power of k times 9 to the power of 1. And if you're wondering how I did that, I just raised individual powers to the coefficient. So again, simplified, this becomes 4 to the power of k times 1/2 over 9k times 9. Now we could bring this 2 down, since it is a 1/2, and multiply to the denominator. And all in all, this gets you 1 over 18 when you multiply these two, times 4 to the power of k over 9 to the power of k, which then leads you to 1 over 18 times 4 over 9 to the power of k. Now this doesn't quite follow the form of a r to the n minus 1, so all you have to do is just do 1 over 18 times a 4 over 9 times the same exact 4 over 9, but this time it's going to be raised to the k minus 1. And so this is basically the same exact thing as this over here, but in this case it just more accurately represents this. Now this is identified as our r, which is our ratio, which 4 over 9 is less than 1. And remember, if our absolute value of our ratio is less than 1, our series will converge. So the form of a converged geometric series is that the sum equals a over 1 minus r, which again, our a is our first term. So we will plug that into this equation that we made, where if our k equals 1, this becomes 1 over 18 times 4 over 9 times 1 over 1 minus 4 over 9, which in the very end gets you 2 over 45. So our second problem will be the infinite series of sine of n over n plus 1, starting at the term 1. Now, like I said earlier, something you want to do all the time is a divergence test first before doing anything else, which is basically just taking the limit of your a sub n into infinity, which we are taking that limit of sine of n over n plus 1. But if you notice, it's kind of hard to comprehend doing this to sine itself, so let's try to take the limit of the inside of sine, which is just n over n plus 1. And you can always do L'Hopital's rule, which just ends up being the derivative of the numerator, which is 1, over the derivative of the denominator, which is just 1 plus 0, which eventually becomes 1. So then if you plug that 1 into the sine, you just get sine of 1. And since that does not equal 0, this will diverge. But again, if it did equal 0, you would have to do a different test, like the integral test, which is our number 3. So we are taking the infinite series, starting at 2, of 1 over k times the ln of k. Now let's make our f of x equal our a of n, placing all of our k terms with x and testing our 3 tests. Is it continuous? Is it positive? Does it decrease? Let's find out. So to prove it's continuous, if you just plug in any value in our bounds, the denominator will never become 0. To prove it's positive, if you plug in our bounds, our x and our ln x will never become less than 0. It will always be greater than 0 because x is positive and our ln x is positive. And finally, to test for decreasing, we can take the derivative of it, but in this case, it's a fraction, so we could just assume that the denominator is always increasing, which if your denominator is always increasing, it will eventually approach a very low number, maybe 0. So now we could turn this series into an improper integral, where you could really just read this as an integral, as the top is infinity and our bottom is just 2, which I kind of said that wrong. This is from 2 to infinity of 1 over x ln of x dx, which, because this is an improper integral, we will plug in a limit as t approaches infinity of our bounds 2 to t of 1 over x ln x. Now when solving for this integral, it's not too complex. It's just a u substitution where our u equals ln of x and our du equals 1 over x dx, which then, if you multiply both sides by x, you get dx equals x du, which, assuming you know how to do a u substitution, you get our limit as t approaches infinity of the integral bounded by ln 2 to ln. And the reason our bounds are different is, again, we performed a u substitution, so make sure you plug our values into that u, or into the x, of 1 over u du. Now this eventually becomes the limit as t approaches infinity of ln, absolute value of u, bounded from ln 2 to ln t. Now this becomes the natural logarithm of ln t minus the natural logarithm of ln 2, which, sorry, I forgot our limit over here. If we plug in our infinity to t, we find out that this just becomes infinity, which of course diverges by the integral test. And make sure to always put that. I forgot to put it in our divergence test, where it just diverges by divergence test. Now let's let our first problem be the infinite series starting at 1 of 1 over n times n plus 1. And the first thing you notice is you could do a partial fraction decomposition on this a sub n. So this becomes a over n plus b over n plus 1, setting it equal to 1 over n times n plus 1. Now again, if you see a partial fraction decomposition possibility in our a sub n, this calls for a telescoping series. I kind of don't know why I drew a sun. That would be bad. There we go. So let's multiply both sides by n times n plus 1, which eventually gets us a times n plus 1 plus b times n equals 1. Now if you set n equal to 0, you get 1a equals 1, which a becomes 1. And if you plug that a into here, and if you set n equals to negative 1, then you get negative b equals 1. So b equals negative 1. So if you plug this all the way back into our a of n plus b over n plus 1, we get 1 over n plus negative 1 over n plus 1, which you could just simply say 1 over n minus 1 over n plus 1, and then take the partial sum of the infinite series. So if you notice, if you keep plugging in terms like a sub 1 plus a sub 2 plus a sub 3, you get 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, etc. Which, again, these middle terms all cancel out, and this negative 1 over 4 cancels out to the next term, which you eventually get led to 1 over n plus 1 minus 1 over n, and then plus that 1 over n minus 1 over n plus 1. Sorry, I meant this was n minus 1. Now eventually these terms cancel out, which these two obviously do, and then this one cancels out inside, and we are left with our outer terms 1 minus 1 over an n plus 1, which we could do a limit of n approaching infinity of 1 minus 1 over n plus 1, which then becomes 1 minus 0, which equals 1. So this series converges to 1 by telescoping. Now last but not least, let's do an approximation problem of an infinite series starting at 1 of 1 over n cubed with error less than 0.0001. Now our r of n, which means our error remainder, is going to be bounded by our improper integral of f of x dx, meaning we have to find an n such that the r of n is less than 0.0001. So let's take our improper integral of n to infinity of 1 over x cubed, which I just translated this 1 over n cubed to an f of x, or x, and dx. Now since this is an improper integral, we'll take our limit as t approaches infinity, replacing the infinity with t, so it's going to be from n to t of 1 over x cubed dx, which then becomes the limit as t approaches infinity of our x to the negative 2 over negative 2, bounded from n to t. Now further evaluating it, our limit as t approaches infinity of t to the negative 2 over negative 2 minus our n to the negative 2 over negative 2. And we could just rewrite that as the limit of t approaches infinity of negative 1 over 2 times t squared minus negative 1 over 2 n squared, which finally, when we plug in our infinity, brings us to 0 plus 1 over 2 n squared. So now let's solve our inequality, since this is going to be less than 0.0001, which is the same as 1 over 2 n squared is less than 1 over 10,000, which is the same, which when we get the reciprocal is the same as 2n squared is greater than 10,000, because since we flipped it, we also flipped the inequality, which becomes n squared is greater than 5,000, which taking that square root eventually gets our n to be greater than 70.7. And with this integer, always round up, even if it was 70.1, into 71 terms, which is our final answer. Thank you for watching.